In this video, we are going to talk a little bit about sigma notation and what it is. Basically, what sigma notation is, it's a short way of writing a sum. That is the addition of a bunch of things in a compact way. So over here, you'll see what sigma notation looks like. If I have a function f of x and m and n are integers such that m is less than or equal to n, then this symbol over here, which is read as the sum as I goes from m to n of f of I. So this is sigma notation over here. So this symbol is an uppercase Greek letter sigma, basically like an S, their version of the S, which is S for sum, right? Then this variable I is called the index variable. There is a starting number, that's this number on the bottom, and then a stopping number, this number on the top. And then over here we have a function of the index variable, in this case I. Although, common ones are J and K, you'll see as index variables here. All right, so that's what sigma notation looks like. And what is it equal to? It's equal to this longer sum over here. This is an expanded form of this here. So you can see the advantage of sigma notation is it replaces this really long formula with a formula that's shorter. All right, and how it would work is that what you would do is start at the starting number down here and plug that into the function for the index variable, and you'll get f of m, and then put a plus, and then increase the index variable, the value of it, by 1. So it was started at m. The next one up would be m plus 1. You would take m plus 1 and plug that in, right? And you would get f of m plus 1, and then put a plus. Then repeat that process. You would increase from m plus 1, you would add 1 to get m plus 2, plug that in to the function, right? And then put a plus. And eventually, since you keep increasing by 1, you'll eventually arrive at the top number, right? Whatever that number is equal to, and you would plug that in, and that's where the sum would end. Okay? All right, so we aren't going to use this a whole lot, just in one simple part where we talk about the definite integral. And all you really need to be able to do is to take an expression that's written in sigma notation and write it in the expanded form like this for this class. In Calculus 2, if you have to take that class, then you will talk more about this sigma notation. All right, so I'm just going to make a few examples where we work through these problems here. All right, it says write the sum in the expanded form and simplify. So the very first thing I would do is plug 5 into the function here, wherever the index variable is. So I plug the 5 in, that's what I would get, right? And then I would put a plus. And then I would increase that right to 6. So now the index variable is 6, plug that in. I would get 2 times 6 plus 3. And then put a plus. All right, then increase the index variable by 1 to 7, plug that in. So the I, plug in a 7 for I. All right, and then increase the index variable by 1 to 8, plug that in. And since 8 is a stopping number, that's where I would stop. Okay. And then, of course, I'd have to simplify all this out. So you can do that however you like. For me, it's just easier to go ahead and do it like this. All of these, I have 2 times 5, 2 times 6, 2 times 7, 2 times 8. So that'll be 2 times 5 plus 6 plus 7 plus 8 You don't have to do it this way. I'm just doing it this way because it's easier without a calculator. And so I have 1, 2, 3, 4 threes. That's 12. And so here I get 2 times 13 or times 26. And that is 54 plus 12, which is, oops, that's 52. Which comes out to be 64. All right, so you can see that this sigma notation is just a compact way of writing this sum right here. All right, let's take a look at the next one. All right, in the next example, I have the sum as j goes from -1 to 3 of 2 to the j. All right, so first they want me to write it in the expanded form. So it's obviously in sigma notation, right? So I would plug in this case, I'm going to be plugging in these values into the index variable j. So the first one would be 2 to the -1. I plug that in and then put a plus. Increase to 0, plug that in. Put a plus. Increase the index variable to 1 and plug that in. So that would be 2 to the 1. Put a plus. Increase the index variable to 2. Plug that in. Put a 2. All right, and then increase the index variable to 3. That is the stopping number, right? So this is going to be the last term in the sum. So I get 2 to the 3rd, just like that. All right, so there we go. We have it written in the expanded form. In this case, right, we can simplify this out. 2 to the -1 is a half. 2 to the 0 is 1. That's 2. That's 4. That's 8. So we get 15 plus a half. Which is 31 over 2. All right. Okay, on the next example. All right. In the next example, we have a couple of variables in here, x and k, but remember you're plugging these numbers, the values of the index variable, into the k, right, into the index variable, not the x. So in the previous two examples, right, our final answers came out to be numbers. That's because the starting point and the stopping point were both numbers, and then the functions that we had of the index variable didn't have any other variables in there. In this case, right, since we have this other variable, we won't get a number as an answer, but we will get some expression. And that's going to be true if, say, your top number, your stopping number, is a variable as well. All right, but otherwise it just really goes exactly like we were doing before. So we start at the starting number, which is a 3. We would plug that into the variable k. So we would get x cubed plus 3 times x. Then put a plus. Increase that value to 4. Plug that in. You get x to the 4th plus 4x. Then put a plus, increase the value of the index to 5, plug that in. And we get this. And 5 was the stopping number, so we would stop there. So you can see what we get here is a polynomial, right, in x is what we get. We can simplify that out and combine any like terms that we have, which we have 7 plus 5 is 12x over here. All right. So these sums, you know, if you have other variables in there, come out to be expressions. This is kind of what we'll need this for in the next video. Okay, so that's all we are going to talk about. Again, we'll only use a very small part of this, and that's really in the next video when we talk about the general method for finding definite integrals.